Hi everybody. So we were here. We started with deep learning, right? Deep neural networks. So one quick thing regarding the project. So please just go on and make your groups, okay? So if you have not done so, please do it. I mean, week 5 is the deadline for submitting your proposal, but you should consider that you should have your group before you be able to submit, right? Because it's a group submission. Yeah. So groups, all groups should be of size 3, please. And then once you have your group, I'm gonna open one submission field on Kirkus, and then you could simply submit one of you just needs to submit the names, and then the TAs will make you a group on Kirkus, okay? So that's regarding the project, and then let's go on with the idea of deep learning. So we talked about the network of perceptrons last time, right? So we started with the idea of we want to do classification, and then this classification, we just looked at it as a kind of realizing a binary function. And when we wanted to realize a binary function of size, with 2 inputs, so we initially could do it for pretty much any operation like AND, OR, but then we got into XOR and we couldn't do that. And the reason was that XOR was, what kind of property it had? Nonlinear, exactly. So it was not linearly separable, so we could not do it. And then we thought, what if we can develop something that makes a nonlinear separation? And then the point was that we could do it again with perceptron, but we had to just cascade multiple perceptrons. And then when we did that, we saw that we can simply somehow separate between different labels for XOR operation. And then we could just build upon that. We just did like any form of classifier. And we said even we can do general, we can approximate any general function as well, right? So that was the conclusion. That was the idea of the universal approximation theorem. And that one motivated many people. Maybe we can just design a good set of perceptrons who can realize what we are looking for, and we cannot describe it by formula or any physical model, right? So this is what we want to do in machine learning. And then we came up with the idea of artificial neurons. So it was basically the perceptron, nothing changed, and a fine transform at the beginning, and then you get one number. But the only difference was that we have no general activation function, right? In the perceptron, you had this step function. In the linear model, you have this activation function to be a line identity function. But now you have a general activation function. And we talked about the possible activations we could have. ReLU is the popular one. Sigmoid, we use it a couple of times in this course. But there are also other versions, right? And then by defining the artificial neuron as a node, which is able to get as many inputs as you want, and then give you one output, one single scalar output, then we can define the neural network. So neural network is basically you make a directed graph whose nodes are those artificial neurons, right? So you have a bunch of inputs. In this diagram, we have 2. We have one output. We could have multiple outputs. And then we just collect a bunch of artificial neurons. We just put them in a specific form, and then we connect them to the input and output. This is going to be a neural network, okay? And neural network, you always move in direction of those, directions on the graph, right? So this is one simple neural network that we have, but usually we don't have such a form. We have a very disciplined form of a structure. Clear? So that was what we did last time. And one point that I mentioned last time again. So from now on, I usually do not mention the weights, but you do know that any of these nodes, anything with a function at the center of it, it is an artificial neuron. And that artificial neuron would get a bunch of inputs. It has one bias, which I'm not showing, but you know that. And then it's going to give you one output, right? And the function on it is the activation function. Clear? So, for instance, F1 How many weights does it have? 2 weights. How many biases? 1. Every artificial neuron has 1 bias. And then these guys are hidden inside this diagram, right? So anything coming from F3 and X2, they are getting multiplied with the corresponding weights, getting added to the bias, and then getting activated with function F1. Okay? Yeah.
Why we are separating the bias from the weight? Technically, bias is also
They are the same thing. Yes, we're going to talk about this later, right? Yeah. I just mentioned it once. I'm going to do it concretely later, but not everybody is at the very initial point seeing that. Okay? But you are right. I mean, at the end of the day, bias is again another weight with a dummy input. Right. So now let's just define a bunch of notions for a neural network. So first thing, depth of a neural network. So what is the depth of a neural network? Depth is the longest path you need to take from input, one single input, towards one output. Okay? If you have multiple inputs and multiple outputs, you have multiple paths, and the longest one. The longest path on your neural network, which you need to start from one input and end up with one output, this is what we call it the depth of the neural network. So, for instance, here, what is the longest path? If I want to get, for instance, from x1 to y, that one is the shortest path, actually, a longest path. It's 3, exactly. So the blue one. Yeah? So I need to get from x1 to f3, from f3 to f2, and then from f2 to f4, and then I have my output, right? So this is going to be the longest path of your neural network. So the depth is here 3. Clear? Now, as your friend mentioned, you could get from x1 to f4. Actually, you can get from one input to one output in even one shot, right? But that is not the depth, right? Because you need to take into account the longest time. So when you want to think of depth, it means that you assume x1 and x2 are initiated at some time, yeah? And you need to wait for an amount of time till all the information has passed through the neural network, right? So if you initiate x1 with some information, some value, say 1, this x1 in the next time instant going to be at the output. That's correct. But you still need to wait so that the information through that blue path is also received at the output. Clear? So the depth is the longest path you need to take on the neural network. Okay? And now, what do we call a deep neural network? A deep neural network is simply a neural network whose depth is more than 2. 2 is not included, more than 2. 3 or more. Okay? So what it says, it basically says what I showed you here is actually a deep neural network because the depth is more than 2. Any questions? No. Okay, so this is what we call it depth, and then the deep neural network is simply something that has depth more than 2, but we usually don't have those weird neural networks with, you know, different connections and somehow random architecture. So usually what we have is a kind of layered architecture. And what do I mean by layered? It means that you have a bunch of neurons who are exactly on the same distance from the previous neurons or from the input. Okay? So I have layer 1, the first layer. Everybody here is the distance from the input is 1. Everybody on the next layer, the depth from that layer to the input is 2. You might have connections like these. So x1 is directly connected to the second layer, but that one is not determining your depth, as we mentioned, right? So even though x1 is directly connected to that guy, still you need to wait 2 layers till all the information have been received at your neuron, correct? So any guy within one layer has same depth from the input, okay? And this is what we call it one layer. And usually what we have a bunch of layers, right, in the neural network. So we have one layer, all of them same depth, and then you have another one and so on, right? So this is the layered architecture, and one layer, a subset of neurons who are exactly in the same distance from the input. Now this is now something that you pretty much, if you just search neural network, you're going to see such a diagram, right? So this is a kind of layered neural network that you have. And now, something that I'm mentioning here is that at the moment you can simply forget about those, dashed connections. We're going to talk about them, and you gradually see that you can have those dashed connections as well, right? But for the moment, in general you can have, but for the moment, just to start building your understanding of neural networks, you can simply forget about that, and you can just think of everything going forward, which is the forward neural network. Okay? Now, if you have a layered neural network, we usually give a name for each layer. We have something called input layer. So this is basically the layer which includes all the inputs to your neural network. One thing that is very important here is that you do not have, it's recording. So you do not have a neuron there, right? So input layer does not contain any artificial neuron, and that's clear to you, right? X1 to Xn, all of those green nodes, they are not neuron, right? They do not do any process. This is the value you give to your neural network, right? It's 1, 2, 3, 0, some number. Clear? So, but we still call it a layer, and this is input layer, okay? Then you could have some output layer. That output layer is actually the layer which is determining the output for you. And that output layer contains neurons, right? So these are the last neurons whose output is actually determining the output of your model. Clear? This is the output layer. And anything between these two, any layer in between, we usually call them hidden layer because they are hidden from the eyes of anyone sitting at the input or output. Everybody's clear? Yeah? So, now, looking at this guy, what is the depth? Can you tell me? I've written here for you. Yeah, you do know it. But do you see that? Yeah? So, if you want to get from input to the output, what is the longest depth you need to take? Or longest distance? You should start from the input, go to the first layer. This is the first jump, right? The second jump is from the first layer to the second layer, and so on till from the last layer to the output layer, correct? Yeah.
So it seems like there's a node actually go backwards to the previous
Yes,
layer.
yeah, that one, yeah.
Shouldn't it become like a, I don't know, like a...
It's a recursion, yes, you could have that one as well, right?
So
So the output of one neuron could be input to another neuron in your architecture, backward to in architecture through time. That is correct.
Okay, and we're counting the depth. We just
No, we ignore that, yes. This is not something, you do not call it depth. Yeah, well, you're going to see this is actually happening in another dimension. So I'm just mentioning here, what you see here is not exactly what you have inside your recurrent neural network, really, because that one is happening in the time dimension. But in general, you could have that one as well. This is possible, but we don't take it into account as for depth. Yeah. Okay. So now what you can simply say is that the depth is simply the number of layers that you have in your architecture, hidden layers that you have in your architecture plus one. And that plus one is simply the output layer, correct? Everybody's clear? Yeah? Now, I told you if depth is more than 2, then it's a deep neural network. Now, if we have a layered neural network, the classic one, how many hidden layers do we need to call it deep neural network? 2. 2 or more, right? Great. So you got the idea. So a deep neural network is simply a neural network who has more than one hidden layer, right? So one hidden layer is still not deep. This is what we call a shallow neural network. But anything beyond that is going to be deep neural network. Okay? So that's it. Now look at this architecture. This is what we did to realize the XOR, correct? So we talked about this last time. So if we give x1, x2 to be any pair of binary numbers, then if we design this, the weights and biases here in all of these nodes properly, then the first one could just realize OR, the second one could realize and var and complement, and the last one could realize n, and all of them together are going to realize for you the XOR function. So the output of this neural network is going to compute the XOR of x1 and x2 at the input. Now, here in this one, what is the depth? 2. And is it a deep neural network? No, it's not a deep neural network. So at some point, when people thought about neural networks, they were always saying, OK, we have some inputs. Maybe we do some middle computation, so we have one hidden layer. And then we do as much computation as we want, so very wide hidden layer. And then after that, we are just doing the next kind of computations. And then this is going to be the output, right? So the only thing we need is one input, one output, one hidden layer, right? But then, as you're going to do it in assignment 1, you're going to see that if you, instead of doing this, you think that, OK, instead of that, I have multiple hidden layers, then you actually can do exactly the same thing, but with much less number of neurons that you need. And this is going to be implemented much more efficient. And this was why people started to call anything more than one hidden layer deep. Because at that point of time, before they start coming up with this idea, OK, maybe we can add more hidden layers, they were, based on the universal approximation theorem, they were thinking, OK, we just need one hidden layer, and everything should work, right? And then they thought, OK, if we want to really do gradient descent, that is easier to do it with one hidden layer, so maybe we stick with that one. So people were stuck at that point for quite some time. And that was the shallow neural network. Then people started to see that if we just add more hidden layers, it's going to make us more strong. It gives us more power to realize different functions. And you're going to do one simple example in your assignment 1 where you can see that you can realize one very long binary function either with an exponentially very large number of neurons in one hidden layer, or you can use multiple hidden layers, and then you're going to have a linearly large number of neurons. And this is going to be a huge difference when the function has too many parameters. Okay? So, moral of the story, deep neural networks, they are simply neural networks which have more than one hidden layer. And if you want to just get back to the terminology we started with, what is a neural network in general? So it's a parameterized function, which we called it a model, right? So we had 3 components, data set, model, loss, and neural network is simply a model, right? And any model has 2 types of parameters. What were the parameters? Weights and biases are one kind of parameters. We call them learnable parameters, right? And hyperparameters, great, yeah? So what are the hyperparameters in one neural network? What is the number of layers? Yeah? Yeah. What is the width of each layer? What are the activation functions? These are all hyperparameters, right? You need to choose them before you can have your neural network, right? If I tell you you have a neural network with some hidden layers, it doesn't make you cannot write it down, right? So you need to know, like, you have 2 hidden layers. Each hidden layer has, I don't know, this much of neurons in it. And then the activation functions are all ReLU. And at that point, you can write it down, right? And then you are left with a bunch of biases and weights, which you need to just learn them. And they are the learnable parameters, right? And if you are going to do the training of this neural network, you simply get your data. You try to tune those weights and biases such that it is going to realize what you are looking for, meaning that it just minimizes the empirical risk. Clear? So this is going to be the whole story of the neural networks and actually deep learning. And one thing that we can do, we can just do first one simple example. Just look at this guy. And let's just try together to find out how many parameters we have here. Okay? So now, first of all, if I talk about hyperparameter, okay, the fact that I'm using 4 different neurons in this architecture, this is one hyperparameter, right? I could have used 5. I could have used 10, right? But if you want to compute the output of this neural network, you exactly need to know how many neurons I have, what is the exact activation for each of them. You do need to know that, right? How do you connect them to each other? This is something you need to know, and this is hyperparameter. But what about the learnable parameters? How many of them do we have? Yes, can you compute it on this diagram? Yeah, what is the number? Close. What is it? 14. Yeah. So let's do it together. So what about F1, F2, F3? How many inputs do they have? 2, right? So when they have 2 inputs, it means that each of them has 2 weights, right? So it is 6 weights up to now, right? How many biases they have? Each of them has 1, so 3 biases, going to be 9, right? What about the last one, F4? It has 4 inputs, right? So 4 extra weights, 1 extra bias, it's going to be 9 plus 5, it's 14, right? So it means that when you go ahead and do the computation, you're going to have 14 different learnable parameters, 14 weights and biases. And the whole thing you do, you just get your data set, put the input, look at the output, compute the empirical risk, and try to find a set of these weights and biases, such that it makes the output similar to the labels you have in your data set. Clear? Great. Okay, if that is clear, now we can finally define deep learning. So what is deep learning? Deep learning is any machine learning where you use a deep neural network as your model. That's it. Okay? Nothing different. So if you are considering a deep neural network to be your model, then you're basically doing deep learning. Yeah? So deep learning is a kind of, whenever you do a learning task using a deep neural network, then you are basically doing deep learning. And then just to make the terminology clear for you, when we talk about machine learning in general, it simply means any kind of learning task we are doing. Yeah? So you could have any sort of data set, could be supervised, unsupervised, even reinforcement learning case. These are all machine learning, right? And you could have any sort of model. Your model does not need to be necessarily a neural network, right? It could be another, model, like a simple linear model. It could be a very weird polynomial model. These are all machine learning, okay? But when we talk about something, I called it before, representation learning, we are basically focusing on a sort of machine learning problems where we need to come up with a sort of nonlinear model which can describe nonlinear functions. Yeah? This is the idea of representation learning. So starting from a general realization, when we just saw the XOR example, then we said, oh, we need something nonlinear, so we need to just find out how we can represent a nonlinear function, right? And then we need to just focus on types of models which are able to describe nonlinear models, okay? So when you are doing that, then you are basically doing representation learning, okay? Now, does a deep neural network represent a nonlinear function? Does it? Can it? It can. Nonlinear function. Can a neural network represent a nonlinear function? If we use it, can we represent a nonlinear function? Yes, we can do it, right? Clear? So when we are doing deep learning, what we are doing, we are using neural networks which are able to do nonlinear functions, right? Clear? So this is why if you check any textbook, they're going to tell you that deep learning is a subset of representation learning, is a subset of machine learning. Yeah? Because machine learning talks about anything general. In representation learning, you are focusing on nonlinear functions. And in deep learning, you are just focusing on neural networks which are still able to do the nonlinear functions. So deep learning is much smaller set of or area of models as compared to the representation learning. But the good thing about the deep learning is that it has been shown to be, its result has shown that they are very sophisticated models. So you basically don't need to go ahead and find other kind of models, right? deep neural networks are fine enough to do all of it, right? So this is the good subset of representation learning. This is why we don't have anything about representation learning anymore, at least in this course. Okay? Everybody's clear? Any questions? No question? Yeah.
I guess I had another question.
Yeah.
Does the architecture or the structure of our model, can that count as a hyperparameter?
Yeah, you can take it as a hyperparameter. I mean, in a structure one, you usually don't do it because if I tell you I'm using a convolutional neural network, you already know how I connect everything, right?
Oh, yes. So
Yeah. It's somehow hidden inside the information I give you. But this is a part of hyperparameter, right? So it's something you need to know to be able to write it down, right?
Yeah.
Okay. Okay. Questions? No questions? Yeah.
What's the intuition behind deep? Like, why the more deep you go, the better?
Yeah, this is what I try to explain, but I mean very intuitively.
Experimental thing or
No, you can show it. I mean, your assignment one, you are going to see it. But if just if I want to put it very simple, say you want to represent one very nonlinear function. And then it turns out if you have just one hidden layer, in that hidden layer you need, 1,000 neurons to be able to do that. But if instead of one hidden layer you do it with, 5 hidden layers, then instead of 1,000 neurons, you just need, 5, 6 neurons in each of those layers. So in total you have here 20, 30 neurons. But in that case you need 1,000 neurons to do the same thing. So when you go in depth, you're just increasing the power of your model exponentially. And this is the main reason that we got interested in deep neural network. Yeah. There is a theoretical reason behind it. And if you just do the first assignment, you're going to see a simple calculation you do, you see that how different it makes. One of them needs to increase linearly in terms of neurons. I mean, the number of neurons should increase linearly with the number of inputs, whereas the other one needs to increase exponentially. And this is not really feasible in practice. So, any questions? Everything clear? Great. So, if you got no questions, so let's just wrap up everything. So, what we had up to this point is that we do know the main components. And we do know what is a deep neural network. It's basically a network of artificial neurons, which we treat it as a model. And the last thing that has left here is that we get a loss function, we compute empirical risk, and then we try to train that neural network. And this is the whole challenge. This is the whole mathematical challenge that you get to deal with in deep learning. So the whole idea is that how we can develop one algorithm which can minimize the empirical loss or empirical risk, actually, not loss here, empirical risk efficiently. Okay? And this is going to be a very hard problem because in practice, if you have a deep neural network, then say, for instance, ResNet. ResNet is a kind of, you're going to see it in Chapter 5. ResNet is a kind of state-of-the-art model that we can use for many classification problems. Okay? And in ResNet, you have 10 to the power 7, 10 million parameters. Okay? And if you want to minimize the empirical risk, it means that you are minimizing a function of 10 million variables, right? And you cannot simply do it by taking derivative and put it equal to 0, or, for instance, guessing the point, the right choice. This is not possible, right? So the only way you can do it, you need to develop one algorithm which can lead you towards one set of ways which are somehow minimizing your empirical risk. And this is what we are going to look for. So the key things that we need to just address from now on are these two things. One of them is how we can develop one algorithm so that it does the training job for us properly or efficiently. And the second one is that how we can choose a right hyperparameter. And anything from now on is basically about that. So I'm just telling you, like, MLP is a kind of architecture. Basically, I am giving you a bunch of hyperparameters, right? Put your layers like this, connect them like that. And then once I specify the hyperparameters, then you need to know how to train it. Oh, you need to use gradient descent. And to implement it efficiently on a neural network, you need to do backpropagation. So anything that we are going to talk from now on are basically within these two classes of questions, okay? And the only last piece of background that you need to know is the idea of gradient descent, which I want to just talk about it right now. And hopefully, if I am fast enough, I can finish it today or maybe on next Tuesday, okay? And then that's it. We're going to have all the background. We can start just exploring one by one different architectures, okay? So should I start with the gradient descent? Any questions? No questions. OK, great. So let's go on with the gradient descent idea. So the whole idea, as you know, as you got from the discussions we had up to this point, is that when we want to do training, we're basically doing a function optimization, right? So we have one function. That function is the empirical risk. We talked about it. You basically get your loss function. You look at your model. You give one by one the data points inside your data set to your model. This model is giving you one output. So I'm showing it with f of that model. And then the data point itself has a label, right? And your loss is going to tell you what is the difference between the output of your model and the label. So you compute that loss for every single point. You add them up. You average them. Then this is only a function of the weights, right? So here in this argument, when you look at f of h, this is basically, we said it's a model. But right now, from now on, we are always talking about the deep neural network. And that h is basically the hyperparameters. You can think of it as a list of information, that it is a fully connected neural network with 3 hidden layers. Each layer has this much of neurons, and this is the activation function, and so on and so forth, okay? This is a list of information. Once you have that list of information, you can draw your neural network, yeah? And then what is W? W is basically those weights and biases, right? Every single neuron in that has a bunch of weights and biases, and you need to just tune them, right? So that's going to be your model when we are talking about deep learning, and X is simply the data point, Y is the label, and L is your loss function. But it doesn't matter really what they are at this point of time. I mean, we're going to talk about how exactly you choose them later on when we get into real problems. But the point is that at the end of the day, I can just forget about anything after the second equality, right? I can simply think about the first term. I am minimizing one function in terms of the parameters, the variable inside the function, right? And I need to develop one algorithm which can do this job for me, okay? So basically, I'm just doing a function minimization, and the only thing I need to know one algorithm to do it. Now, before we start, let me just define you 2 terms. The idea of a global optima or global minimum, and the idea of local minimum. So if you look at this function, and from now on, whenever I talk, when it's easier for you, just think of W to be one single parameter, okay? Just think of one weight. Then this function is going to be a scalar function that's going to be easier to visualize everything. And then we try to just expand everything to higher dimensions as well. So if you think of that, W to be just one single parameter, then this function R hat is going to change. The risk that you get is going to change when you change the value of the weight inside your neural network, right? And this could be very deep at some points. It could be high at some other points. But this usually, when you have a very deep neural network, is not going to simply behave like a ball, right? It's going to just behave weirdly, right? And then when it behaves, goes ups and downs, then you're going to see that there are a bunch of balls in your risk function, right? And each of those balls is a minimum as compared to everybody around it, right? So in its neighborhood, it's the minimum. This is what we call it a local minimum. Okay? So it's locally minimum, meaning that anybody in the neighborhood is larger than that. So if you change the weight slightly in the neighborhood, you're going to get higher risk. But it doesn't guarantee that this is globally minimum, right? Maybe when you get out of one neighborhood and you get into a new neighborhood, then you're going to see much smaller risk, right? So the global one means that if you just go and search every possible weight, yeah? So meaning that, like in this example, if I just look after everybody on the real axis, then this value which is giving me the least possible risk, that is the global minimum, right? Now, what do we like when we are training? To get to the global one, right? So we do like to get to the global one, but where do we get usually? We usually get to the local one, yeah? Because as you're going to see, when we develop one algorithm, we are in practice unable to get to the global one. It's impossible with deep neural network, yeah? You cannot do it, right? Just think of a landscape with lots of, hills and ups and downs, right? It's pretty much impossible that you can tell me I am at the highest or lowest point of this landscape, unless you are able to just explore all the landscape, right? And you can think that if your landscape is like 100 dimension or 1,000 dimension, or as in ResNet 10 million dimension, then it's pretty much impossible to explore all of it, right? Okay? So the whole idea, as I told you, is to just develop one algorithm which can start from one point. Okay? Initially, I just put my weights to be something. And then this algorithm is able to gradually change the weights up to the point that it at least gets into a local minimum, right? So some point where everybody around it is higher, right? So this is what I'm looking for. And you might ask me, okay, what is a big deal right here, for instance? Just look at this real axis, right? And then try to grid it. Yeah? Say, I don't know, from the function at the end, the weight at the end of the day would be something between what? -10 and 10. So start from -10 to 10, make 200 grids, and see what is the value of function in each of these grids. Then take the grid which gives you the minimum value, right? So it is the minimizer, and this is totally right. Yeah? This is what we call the exhaustive search, right? I give you a function. You want to find the minimum. You don't need to use any gradient descent, any KKT, nothing. You just get the interval where you know your variable is changing. You just grid it, make a fine grid on it, and then you check the value of function in each grid and take the grid which is giving you the smallest value, right? Smallest sample. And that grid is going to be a good approximation of your minimum, correct? But the point is that you should think of dimensionality here, right? So if your function is d-dimensional, what does it mean? How can you make the same fine grid? Say I have one-dimensional function, and I make 10 grids on it, okay? Which means that starting from the first point to the second point, I have one fixed distance, right? Say I'm looking in one interval of length 1, okay, from 0 to 1. And if I make it a fine grid of length 10, of 10 grids, then the distance between every 2 points on this grid is 0.1, correct? Now, if now my function is two-dimensional, and I want to have as small grid as before, how many grids should I make? Look at this. So I told you this is one axis, right? And I start from here, I end up here, and I make a couple of grids, right? So the distance here is fixed, correct? Now, if I want to make, now I get into the second dimension. And I want that now my grids are not going to be on one axis, right? So it should be in all of this surface, right? Correct? Because this guy changes from 0 to 1. This other guy is changing from 0 to 1. Now, if I want to have the same distance between my grid points, how many grids should I do? 100, exactly. So I need to make same grids here, right? And then any point here is one grid, correct? Correct? You got the idea? So anything here is the same grid. So I have 10 grids here, 10 grids here, and the total number of points in this surface is now 100, right? What if I go for 3 dimensions? 1,000, right? Fourth, it's going to be 10,000, and so on, right? Now, if I have G grids in general in 1 dimension, now the number of points I need to check, it's going to be G to power D. And I told you what is the value of D if I think of ResNet? 10 to power 7, right? So say this G is even 2, okay? 2 to power 10 million. Yeah, it's impossible, right? It's practically impossible. I mean, it's by orders of exponent larger than the age of this universe, right? So you cannot do it. It's impossible. So this is the curse of dimensionality that we have when we are dealing with a very big model. We cannot really do a simple thing which you always think of it in small dimensions. Yeah. This is why we are looking for an algorithm. If I could grid this space, I would not take your time and my time to talk about gradient descent here. We cannot do it. Yeah. So grading anything of like exhaustive search is impossible. It's exponentially complex, very huge. We cannot do it. So we need to go for one algorithm. So it's practically impossible, and this is why we are looking for something called optimization algorithm. So what is the optimization algorithm? One optimization algorithm, which usually people in machine learning or in deep learning mostly, they call it an optimizer. So an optimizer is simply one algorithm, one algorithmic approach, which starts from one point, so you can start from any point in this algorithm. And this algorithm is gradually taking you towards the one local minimum. Yeah? So one point, it's just taking you towards one point, which is smallest within its neighborhood. I mean, of course, you cannot guarantee usually that this is the smallest within the whole space, but you can say within anything around it is the smallest value. Okay? Now, if you want to think of some visualization of one optimization algorithm, you can always think of this diagram. So you have this function, and what you want one mechanism, one strategy. They start from one initial point, like this point, the gray point here, as you see, and then the algorithm is telling us how we should move. So it says like go forward, and then we come forward a bit, and then we get into a new point, and we check the value of function. The value has increased, right? So this is one step. And then again, the algorithm tells us, okay, keep on going, and then we go forward. And then it again tells us keep on going, but slower. And we keep on going slower and slower till we end up after a finite number of steps to the local minimum, right? So this is one optimizer. One algorithm which is gradually, iteratively pushing you toward one local optimizer or optimal point. Usually we think of minimization. So, yeah.
Can the optimizer be not greedy? I mean, like, don't always take the best step. Like, you can to find the global, like simulate the meaning or something.
No, how do you? I mean, unless you have a very nice properties in your function, you cannot do it. If you do know, like, for instance, I'm going to shortly mention. So if you have a convex function, which means that you do know that you have only one minimum, which is both local and global, then yes, if you use any optimization algorithm which is converging, is moving you toward the global optimum. But if you don't have it, which is usually the case in practice, then you cannot do it. No. So, any questions? Everybody's clear? No? Okay. So this is what we call it an optimization algorithm, and maybe we can write it down in a bit of algorithmic form, right? So how does it look like if we want to write it down in an algorithmic form? So let's consider that we start with some initial point. So the initial point is the initial set of weights we have in our neural network, right? So randomly just give some weight to each edge in your neural network. That is W0 here. And this W0, which is the initial point, is going to give you a bunch of outputs, right? So if I set my neural network with those weights, then when I give my inputs from the data set, it's going to give me some outputs. And those outputs are very bad outputs. They are very different to my true labels, right? And then when I compute the risk is very high, correct? And then the thing that I want to know, okay, how should I modify every single of them? Or say this whole vector, how can I modify it into a form of a new vector, which next time when I repeat the same thing, it gives me less empirical risk. Clear? So this is the initial weight, and I'm initiating this delta to be infinite. Delta, what is it? This is somehow I am thinking of, delta, is the difference between the risk I had in the previous step and the risk I'm seeing right now. Okay? The difference between the value of function in the previous step, empirical risk in the previous step, and this step. Okay? Now, initially I set it to be infinite. Okay? Now, I also consider one very small epsilon. So this epsilon is actually the limit where I am going to be unhappy. Meaning that because when you start to gradually move toward the local minimum or any minimum, you're not going to stop, right? You always want to go a tiny bit closer to that, right? If I start from here and I say I want to get to that wall, but first I'm going to step on the middle, and then after that I'm going to step on the middle of this middle, and then I'm going to again step on the middle, I would never touch the wall, right? So it never happens. But I would get, if I get very, very close to that wall, I'm fine, right? So this is what the epsilon means. So I want my function to just change this very tiny bit in a couple of iterations. When I see that the function is not changing, then I would say, okay, pretty much I'm at the minimum point, okay? And now what do? I start to find some mu, some vector mu, which is exactly of the same dimension of my weight. Like my weight has 1,000 entries, so I have 1,000 weights. My vector mu has 1,000 entries as well. Clear? Now, what I want to find this mu such that I could update my weight. So my next weight is going, so I told you, I have the initial weights, I send the data, I compute the risk, I compute the average loss, correct? And now out of that, I want to find some idea, I make a new mu, okay? And now I add this mu to my previous set of weights, meaning that every single weight is going to be added to the corresponding entry in mu. And now this time, again, when I'm sending the data, I'm going to see less risk. So I'm looking for that mu. You get the idea? So I'm looking for this one. And then every time that I update, I am going to just check how much my risk function is changing from previous, as compared to the previous step, previous iteration. Like initially my risk was 10, now I changed my weights, it got 9, so I just dropped by 1. And then next time I change my weights, it's going to be 8.5, so I drop by 5. Each time I look at this value, how much I've changed. Yeah? Now, the kind of properties that I'm looking for, one of them is that, as I told you, most of the time, not necessarily all the time, but most of the times, when I do this update, I get a smaller risk. Yeah? I would be fine if I just get a bit of higher risk and then drop. That's fine. It's okay. Right? But at the end of the day, I want most of the time to decrease, right? So this is one point that I want to have. And one other thing is that I want my algorithm to stop iterating within a feasible number of steps, okay? And when does the algorithm stop? The algorithm going to stop when I see that this difference I'm updating in each iteration is being smaller than the threshold I considered, right? So I would say that, okay, if I am not changing in multiple iterations after each other more than 10 to the power minus 5, then I'm going to stop. Yeah? I assume that I have reached the point which is minimum. Okay? And I want that this happens within a finite number of steps, like, I don't know, I have 100 iterations, and then it's a stop. It doesn't go forever. Yeah? So these are the two key properties that we are looking for. And basically, any sort of optimizers we have in deep learning, you can always write it down in this form. The only key point is that how you can choose this value of mu. What is this vector mu? How you can find it. Yeah? And the key point is that this mu should always be proportional to, anyone has any clue? Gradient, minus gradient, right? If you are doing minimization, it should be proportional to the minus gradient. So you should move in the opposite direction of your gradient. If you can do it in each step, then you are basically dropping in each step. And at some point, you are going to stop. Okay? So this is the whole idea of the gradient descent. And we have a lot of optimizers. We're going to see them in chapter 3. But all of them, at the end of the day, compute this mu proportional to the minus gradient to some different form. Okay? Any questions? Everybody's clear? So now, as I told you, this mu in practice, so it turns out that this guy should be proportional to the negative of the gradient of your function computed at the point wt minus 1, the point, the weights that you have already. So you need to compute the gradient of those at those weights and then just make it negative and then add it up to your previous weights. But I want to make it clear for you why this is the case. Yeah? So I could just stop here, say, OK, minus gradient, bye-bye. But we're not doing that. So we just want to understand why we should move towards the minus of the gradient. What is specific about that? OK? So if you got now questions, then we can have just 5 minutes breaks and then we're going to continue. OK? Okay, shall we go on? So, maybe a bit of review over derivatives. I'm pretty sure all of you know that, but just to be sure that we are on the same page. So, derivative of a function, I mean, everybody knows what is derivative, right? So, derivative of the function fx equal by x is? What is derivative of fx equal by x? 1. X squared, 2x, right? 2x. X cubic, x3. 3x squared. Okay, everybody knows what is derivative. That's fine. So this is the definition, right? So the definition of derivative of a function is simply the value of function at one point minus the value of function at a very close by point divided by the size of the step you have taken, right? So if you want to look at it from a geometric point of view, say I have this function, this is my f of w, and then the variable that I do have is on the x-axis, so here is w. What do? I think that I am on one point w0. I am at this point w0. I assume that I just move with very tiny bit of a step forward, right? So when I move a tiny step forward, then I'm going to hit a new point on the function, right? A new second point, so the second line, as you can see. And then in that case, the value of my function in this tiny move has changed with dy. And this dy doesn't need to be necessarily very small, right? So you can move very tiny bit, but it could just boom up, correct? And then the ratio of this dy to dw, the ratio of the increase or decrease in your function divided by the step size you have taken, this is what we call a derivative. And everybody always has this feeling of, like, intuition that this is the slope that you have and the tangent of your function, right? When you touch the function, the slope of that line is your derivative, correct? So this is the idea of having derivative, but there is one cool thing when we think of one-dimensional derivative about that. Now, look at this one. When I am changing or moving forward very tiny bit, then my function is increasing, right? What's going to be the sign of my derivative? It's positive, right? So when I am thinking of a one-dimensional case, what can I say? What are the directions I can move in one-dimensional axis? Just I have two directions, right? I can either go in the positive direction or negative direction, correct? Now, here the gradient is positive, and what does it say? It says that if you move in the positive direction, your function is going to increase, correct? Okay, that's good. Now, what if my function decreases when I move in that direction? What is the sign of the gradient? Negative. Now, if I want to increase my function, in this case, in which direction should I move? Now, here at point w0, look at it. So if I move toward dw, if I move toward positive direction, my function is going to decrease, right? So if I want to increase my function, which direction should I face? The opposite, the minus, right? So I should go to minus. And minus is exactly the sign of my gradient, right? So again, the gradient in this case it's telling us it's negative. So if you want to increase your function, you should move in the negative direction, correct? So this is the idea. Your gradient, or your derivative in this case, is just showing you the direction that you need to move in order to increase your function. Clear? Everybody got the idea? Great. So derivative shows the moving direction, side that your function increases. Now, if instead of increasing your function, you want to decrease your function, what should you do? You should just do what opposite of what the gradient said, right? So if you want to just move in the direction where your function decreases, you just need to move in the negative direction of your derivative. Clear? Great. Now, can I have my derivative 0? At minimum, this is one choice. What else? Maximum. So I could have my derivative 0 when I am at the maximum. Okay? Now, look at this guy and tell me this. So let me draw it here for you. Now, you see where the function is maximized, correct? In the diagram, in the figure. Yeah? So that is the point W max, right? So this is W max. Now, here is W. Here is, you have FW there, right? I want to show the derivative here. And by the way, I forgot to indicate this. So here in the notation, you see, sometimes I usually show it like this. So F dot. And by dot, I simply mean the derivative, okay? So some people use prime. I use dot. It's going to be easier, okay? So F dot of W is the derivative, okay? Now, here. Now, when I am behind W max, okay, anything below W max, what is the sign of the gradient? It's plus, yes? It's going up, correct? So if I want to draw F dot, where should I draw it? Here or here? Up, right? So it's going to be plus, correct? Now, it's going to be plus. It's coming down. Where does it get 0? At W max, right? So at the W max, my gradient, my derivative is exactly 0, correct? So it means that when I'm drawing the derivative, it's going to hit here, correct? At W max. Now, after W max, when I just move forward, what's going to happen to my function? Does it increase or decrease? It decreases, right? So what would be the sign of my derivative? Negative, right? So after this W max, after this point W max, should I have my derivative here or here? Below, right? It's negative, correct? Clear? Now, if I take derivative of this guy again, would it be positive or negative? Negative is dropping, correct? So when you are at the maximum, your derivative is first positive, as you can see on the board, and then it gradually reduces to 0 where you touch the maximum. And after that, it's going to be negative because your function is decreasing. And if you again take a derivative from this guy, that should be negative. So your second derivative is going to be negative. Clear? So if you have a function and you take the derivative and you find the point where the derivative is 0, then you can take the second derivative and check the sign of that second derivative. If that one is negative, then it means that your function has a maximum. Clear? Everybody's clear? Yeah? Okay. Let's try it for the case where we have a minimum. When we have a minimum, we have, again, the derivative 0. Correct? So here is the point W min. Clear? Now, this is minimum. If I start behind W min and I keep going, what is the sign of the derivative? It's negative. I'm dropping down, right? So where should I draw it? Here, right? So I'm going to draw it like this. This is some derivative. When I get to W min, it's going to be 0, correct? Because at W min, I am horizontal, right? So here it's 0. What's going to happen after W min? It's going to keep going up, right? So this is positive. I should draw it like this. Clear? Now, if I take derivative of this function again, what is it? Positive or negative? Positive. Clear? So again, if you have one minimum, before minimum you have negative derivatives. After minimum you're going to have positive derivatives. At the minimum you have 0 derivative. Your derivative is always increasing. So if you take the second derivative, it's going to be positive. Again, you just find the derivative, put it equal to 0, and then after that you check the sign of your second derivative. And then if it is positive, then it is a minimum. Clear? Everybody's clear? You got the idea? Great. Now, can you think of any other form of points where we have derivative 0? Inflection, right? The inflection point, exactly. So this guy, correct? So you could have your function just going with a curvature like this, going up, And when it gets to this flat curvature, it's not going down again. It's just going up again. It can't happen, right? Or it's just coming down, and then it gets to the flat curvature. It again goes down. So here you are going to have the curvature changing, right? Up to this point, it was like a bowl. After that, it's going to be like a cap, right? So this is what we call it inflection. And if you compute the derivative here, we're going to have this kind of point. So let's just look at this one. So say I have inflection point. So this is Wnth. And now, when I am before the inflection point, when I move forward, what's going to happen? It's positive, right? The gradient is going up, right? So, sorry, the function is going up, the gradient is positive. So I'm going to draw it like this. So it's going to get to 0. And then what's going to happen after I pass the inflection point? Still I'm going up, right? So I'm still going up like this, right? Now, if I take the derivative of this one again at this point, what it should be? 0, right? Because if I think my function is smooth, then it should have the curvature flat. Everybody's clear? Yeah? So this is going to be the case. So when you have inflection point, your function is increasing, it gets flat, it again increases. Or it could decrease, gets flat, again decreases. In that case, you're going to have something like this, right? But in both cases, at that particular point, the derivative function is again flat. Yeah? And this means that your second derivative is going to be 0, right? So probably this was the idea you had when you were high school. So if they give you a function, tell you find the extreme points of this function, you just take the derivative, check the points where this derivative is 0, and for each of them you check the value of the second derivative, right? And this is going to tell you whether it is positive or, it is a minimum or maximum or inflection point. Clear? Great. So now we can just extend the same idea when we have a multidimensional function, and we only need to get the idea of partial derivative. So if I have this function, which is a function of multiple variables, so if I have this function f, let me just try one example here. Say I have this function f, which is a function of two weights. So it's f of w1 and w2. And then this is, for instance, w1, w2 plus w1 squared. Okay? If I want to take the partial derivative with respect to w1, what it would be? What is the partial derivative of f with respect to w1? What is it? It's going to be w2 plus 2w1. So when you are taking partial derivative with respect to w1, you treat the other variables, w2 for instance here, to be a constant, right? So w2 is a constant, so w1 times w2, the derivative is going to be w2. It's like w2 was 5, right? So 5w1, the derivative is 5, correct? So it's going to be w2 plus 2w1. And then what is the partial derivative of f with respect to w2? What is it? w1 only, because here now w1 is the constant, w2 is the variable, so it's going to be w1, and then the derivative of this guy is going to be 0 because it does not depend on w2. Clear? Now if I have a function which is a function of n different variables, how many of those partial derivatives do I have? N, not n by n. I mean, here I had 2 variables, so I have 2 partial derivatives, correct? Don't confuse yourself with the second derivative. It's the first derivative, right? So your function, your function is a scalar. Okay, so I think this is something you're getting confused. So my function is a scalar, correct? So it gets the whole weights, and then it gives me one number, correct? Then the derivative is going to be, like you have n different derivatives, correct? So if I have one function, so this is a good point your friend mentioned, just this function f of w, this guy here is a scalar function. It's like your artificial neuron, okay? It gets lots of inputs. It gives you just one number at the output. Clear? Yeah? So this is your multidimensional function. And if it is a function of n different points, then you're going to have n different partial derivatives. Clear? So now, how can I somehow interpret these derivatives? It's again the same thing as before. So what I can say, like if I am within the 2 dimensions, so now you think that I am in this space of W1, W2. So this is the 2 dimensions, right? And if I want to think of my function, there's going to be one axis coming out of this plane, and then the whole function is here, right? So this is where you look at, right? And then if I'm at one particular point W, like this, one vector, I can move tiny bit in one direction, right? And now in this 2-dimensional case, how many directions I can move? 4 is about the components, but basically you can look everywhere in this plane, right? Correct? Yeah? So now is pretty much infinite directions, correct? So you can now move. So it's not like the 1-dimensional case anymore, that either forward or backward, right? You can actually change the angle continuously from 0 to 2 pi, right? And then this guy is very, very tiny bit, right? And what is this dw? Is it a vector or a number? It's a vector. Yeah? What is the dimension of dw? Here is 2, right? If my function is n-dimensional, it's going to be n-dimensional vector, right? So this dw is n-dimensional vector. It means that it's telling you how much you should change the value of your current point in each direction, right? So in this case, for instance, this guy, dw, this is a vector dw1, dw2, which tells you if you are at this point, right? So say I'm at this point, w1 star, for instance, and then here is w2 star, then it's going to tell you, okay, just take step dw1 in this direction. So a tiny bit here, dw1, and a tiny bit here, dw2, correct? And then if I take these 2 points, this is going to be the new point, right? So this is w star plus dw, the vector. Everybody's clear? Yeah? You got the idea? Everybody's cool? Great. So what we can think that we have one vector which has n different entries. Each of them is a very tiny step. And what we are looking for the fact that when we are moving in that tiny direction, how much our function is changing. And if we want to compute that, again, we can use the partial derivatives. Okay? We can use the partial derivatives. I get the partial derivative with respect to each variable, multiply it to the corresponding step, and then sum of them is going to be my change in the original function, right? Everybody's clear? Yeah? Great. So now let's start from this idea, this definition, that the change in my function is basically this summation, and then make the gradient vector. Okay? How we can do it? I told you that the change in my function is the sum of those partial derivatives multiplied with the step size in each direction. Correct? Now, can I write it down in a vectorized form, this summation? Can I? What kind of product is that? It takes 2 vectors. It gives me one scalar. What is it? Inner product. Great. So I can make 2 vectors. One of them is this one, which contains all of the partial derivatives. The other one is exactly the dw vector, correct? And the inner product of these 2 is exactly the change that I have in my function, correct? So that first vector, which contains all of the partial derivatives, this is what we call it, gradient. Yeah? So the first guy is the gradient vector. So inner product of the gradient vector with the direction or the vector that I'm moving towards, it is going to give us the change in our function. Clear? So the change in our function is being the inner product of the gradient at one point and the movement vector, dw. Now, if you want to have a bit of visualization, you can look at this diagram. So now, W1 and W2 that I had in the board are now in the plane here, right? So here is, for instance, W1. This guy is W2. And the value of function, depending on which point I choose, like here I am at 1, 1, for instance, and then the value of function is something. Yeah, I'm showing it on the in the height axis. Okay. Yeah. And then if I change, this function could change, right? Now I have a three-dimensional landscape. So this is my function, and this is one particular point. So this is W01, the first component of the vector W0. This is W02, the second component. And if I do know them, I can specify the point where I am computing my function, right? Now, I can take that point, just look at the landscape. This is going to be the value of my function, correct? Now, if I want to move, I have one tiny vector. It can move in any direction in this W1, W2 plane, right? So I can move any direction on the ground, correct? And then I'm at this point. I choose to move in this direction a tiny bit, okay? This is what is happening here. But when I do change, then my W, the first entry and the second entry, both of them are changing. And not only they are changing, also the value of the function could change, correct? So the function was like this. So if I move here, then I'm dropping. Correct? Right? And now, if you look at this change and you divide it by the change you have on W1, you're going to get the partial derivative with respect to W1. If again you look at this change and divide it by the change on your other axis, you're going to get your second partial derivative, right? And then if you have that vector of partial derivatives, which we call it gradient, what is the dimension of your gradient? What is the dimension in this example? It's 2. It's exactly of the same dimension of your variable, correct? So this is going to be one vector, again within the same space, right? Same plane, right? So you're going to have two partial derivatives. It is a two-dimensional vector. You can again show it within your W1, W2 plane, right? If you have n-dimensional function, then your gradient is again n-dimensional. You again can show it in your variable space. Everybody's clear? Right? Now, so what does it mean? It means that your gradient is also one direction that you can move towards, right? So I told you when I'm here, I can move into any direction in this plane, correct? Gradient is also one direction. For example, it says this. So I can also move in the direction of my gradient. Cool? You got the idea? Good. So when you have, now what I'm doing, I'm going to cut this landscape, okay? So it's hard for me to always work in 3 dimensions. What I'm going to do, I'm going to say this is my function, right? So you think of hills and, I don't know, tops and hills, things like that. And then I get a knife and then cut it at one specific height. If I do that and I go up and look at it, it's going to be lots of, circles, correct? This is what we call it the contour of the function, correct? In the 2 dimension. And now, say that I have this nice one. For instance, at one height, it has just one top, okay? If I cut it, it's going to be a kind of, circle shape contour, correct? Say it is not the perfect circle. It is something like this, for instance, right? It's the contour. It's where your hill got cut, okay? And now, if I go up and look at this plane, then in this plane, I can see the directions that I can move, and the direction of my gradient is also there, correct? So I can see dw, for instance, is the direction that I decided to move. Also, I can just plot the direction that gradient tells me, correct? Now, the question that I have now is pretty much same as the one which we had in the one-dimensional case. If I want, for instance, to get my function increasing the most, which direction should I move? It should be the direction of gradient, you are right, but how we can say it? Let's do it together. So here we have two-dimensional case, right? So say dw is this guy, this dw, this is one vector, and this is the direction of the gradient. I told you the change in your function is the inner product of these two guys, correct? Now, since we are in two-dimensional space, we can think of the angle between these two vectors. This is what I'm showing by theta here, right? So this is one guy, this is one guy, right? The angle between these two, yeah? And now, if I do know the angle, and say that I do know that my step size is fixed and very small, so I say I don't care which direction I'm moving, I'm always moving very tiny bit, epsilon, okay? So this means that the amplitude of that dw is always epsilon, correct? So I can write the inner product as the amplitude of this dw times the amplitude of my gradient times the cosine of the angle between them. Do you agree? Yes? So you have two vectors, amplitude of this guy multiplied by the amplitude of this guy multiplied by the cosine of the angle between them. This is going to be the inner product when you are in two dimensions, right? Now, if I do that, and I told you that this dw is very tiny bit, so it's always the amplitude, so the size of the step I'm taking is always epsilon. So instead of this amplitude of dw, I can write epsilon, correct? So now, the inner product is going, oh, I don't have the expression here directly. So the inner product is going to be the amplitude of my gradient, which is something fixed, multiplied by an epsilon, which is again something fixed, multiplied by the cosine of the angle between them. Now, if I want this guy to be maximum, which is the change in my function, what should be the value of theta? 0. If I put theta to be 0, then the change in the function is maximized because the inner product is maximized, correct? So what does it say? It says that if you want to just move in the direction where your function increases maximally, just go in the direction that the gradient tells you, correct? Everybody agrees? Everybody okay? Yeah? Now, another question. If I want my function to decrease and decreases maximally, what should I put the value of theta here? 180 degrees or pi, right? So it means that gradient tells me go this way. This is when cosine, if I move that, cosine of theta going to be 1, right? But I want to just decrease it, decrease the value of function maximally. So I'm going to just look backward and then move in the 180 degrees opposite direction, right? And then the cosine going to be minus 1. Now the change in my function is minus that expression, right? And this is the maximum thing I could have if I want to decrease my function, correct? So I can alternatively say that if I put theta to be pi or 180 degrees, so totally opposite direction of my gradient, or negative direction of my gradient, then my function is going to decrease maximally. So I can move in other directions, and my function again decreases. It might be the case, but it's not maximally decreasing, right? So the direction minus the gradient, negative gradient, is telling me go that way, and your function is going to decrease maximally. Correct? Everybody's clear? Any questions? No question? Great. So then this is the same idea as the one I told you in the one-dimensional case. So if you're at one single point and you want to just decrease your function, compute the gradient, right? And then go in the direction minus gradient. Then this guy is going to take you towards one new point, which is decreasing your function maximally. This is basically what we wanted for our optimization algorithm, the optimizer, right? Because in each point we wanted, I give you the set of weights. This is one point on this function, right? And at that point, if you can compute the gradient of the function, which is basically the gradient of your empirical risk, if you can compute that one, then the only thing you need to do is just to move in the negative direction of that. Yeah? And what you know is that you don't know where is the minimum yet, but you know that this is the best direction you can go for, right? So it is pushing you towards the minimum of the function. Yeah? Clear? Cool. So if you got clear, then just let's look at the cases like the one-dimensional case where we could have our gradient to be 0. And by gradient being 0, I simply mean every single entry in that gradient vector is 0. All the partial derivatives are 0. So what are the candidates? Again, the maximum. Why? Because if you get on the top, so it's again flat, right? So if you get a plane and touch this top, it's going to be exactly parallel to your W plane, right? And then moving in any direction is not going to change anything, right? So the change is going to be 0. So one case is when you have the maximum, right? And you can, I'm not going to just derive it as we did for the one-dimensional case. It's going to take a bit of more derivations, and we don't really need it because here we don't use second-order algorithms. But it is good to know that if you compute the Hessian matrix, and do you know what is Hessian matrix? So if you take the gradient, I'm going to show you. If you take the gradient, it's a vector of partial derivatives, right? So you have now n different derivatives, right? And each of them, you can think of it as a function, right? And that guy, again, has a gradient, right? Because that is a function of n variables. So if you take those gradients, it's going to be all of your second-order gradients, or second-order partial derivatives. And it's going to be n. Each of them has n, so n by n matrix, right? This is what we call the Hessian matrix. So it is basically the second-order derivative in the higher dimension. Okay? And then when we have a Hessian matrix, we don't have a number. We cannot check the sign of a matrix, right? Instead of sign, what do we usually check for the matrices? Determinant could be, right? Or the eigenvalues, right? So if all the eigenvalues are positive, this means that your matrix is something we call it positive definite. And in that case, if your matrix is and if they are all negative, then your matrix is negative definite. So I told you for simple function one-dimensional, if your second-order derivative is negative, then you have a maximum. Again, here is the same thing. If you could compute the Hessian matrix, and if you could check whether it is negative definite or not, and it turns out to be negative definite at that point, then it simply means that you are at one maximum. But as I told you, it's too much computations. We cannot usually do it. Okay? Gradient is expensive enough for us in practice. Okay? So this is one point. Another kind of point we could have a minimum, right? And again, at the minimum, if you touch the bottom of a bowl, it's always parallel to your W plane, right? To the plane space of your variables. And then this is again where you're going to have your derivative to be 0, and you can check like what we had in the one-dimensional case. That in this case, the second-order derivative, which is a Hessian matrix, is going to be positive definite. But as I told you, we're not going to use it. So if you don't get what I'm talking about when I talk about Hessian matrix, you can simply forget about this. This is not real crucial. Okay? And we could have another kind of point which happens in the multidimensional case, and this is what we call it the saddle point. So now, what is a saddle point? A saddle point is that, look at this one. Do you know what is saddle? Yeah? So this is the thing you put on the horse and you sit on it, right? This is the saddle, right? So now when you sit on the saddle, okay, the front and the back are top, right? So when I just come down, here is the horse. Here I see a minimum, correct? Right? But when I sit on it, my legs are going down, right? So if I just rotate the horse, look at the horse from back, then I have a maximum. So this is what you call a saddle point, right? So in one direction, when you move, your function is just going up like just seeing a minimum. In one other direction, when you go, your function is staying maximum, right? So this could happen in multidimensional case. This is not the case when we have one-dimensional scenario, right? And there, again, your derivative, your partial derivatives are all 0. And in that case, so this is the kind of saddle point. I tried hardly to show it. So here you have a minimum, as you can see, but it's not a perfect diagram. But in that direction, you're going to have a maximum. And partial derivatives are all 0, but this is neither minimum nor maximum. Okay? And again, here you could have this one, this 0 derivative, but the second order derivative, the Hessian matrix, is going to be neither positive definite nor negative definite, because those eigenvalues corresponding to the maximum direction, they are going to be negative. Those corresponding to the minimum direction, they are going to be positive. So you are not having the same sign for all of the eigenvalues. Okay? Clear? So this is the third kind of things you could have. As I told you, this is the Hessian matrix. So you have your function f of w, and this is a function of n different variables. And then if you want to compute the second order partial derivative, you can compute it for any two possible cases. So any w1, any w2. And because of that, you would have n by n matrix. And this is what we call it the Hessian matrix, the second order matrix. But as I indicated here, we are not using it in this course. There are some algorithms, I'm going to mention it later in chapter 3, that we call it the second order algorithms, which use Hessian matrices, but we don't use them in deep learning because it's very computationally expensive. Okay? Great. So that's about this. And now, what is the moral of the story after all of this thing? The moral of the story is that if you want to just decrease your function maximally, just always move in the direction, negative direction that your gradient is. Yeah? And then what I can do, I can just replace here in this update rule, line 4. So this was the optimization algorithm we started with. We said we want to start from one point. At every single point that we want to just move in one direction, find that vector mu I showed you initially, right? That sends us towards the direction where we are decreasing the function, right? And that direction, we do know what it is now. It's the minus the negative of gradient, right? So instead of that, I just put the negative of the gradient. So if I do know my empirical risk, so I'm at one particular point, wt in one iteration, wt minus 1, say, and then I can compute the gradient at that point. If I can do that, then I'm going to get my w. I just subtract it from that gradient, and then I'm going to have a new vector. That's going to be wt. This is the new set of weights. And that one, as gradient says, it should be smaller if my step size is small enough. It should be smaller in risk as compared to the previous weight, right? So I start from one point, always move in the negative direction of my gradient until I get to a point where the gradient is 0. And if the gradient is 0, what's going to happen in this algorithm? Sorry? Yeah?
I assume we'd be exiting the loop and finishing?
Yes, we finish. What did you say? We don't update at all, right? Exactly, same thing. So if the gradient is 0, then your previous weight is exactly the same as your new weight, right? So you're getting your previous weight minus 0 is the same thing. You're going to call it the new weight. And then you get to line 5, and when you get to line 5, you get the value of your risk in the new weight minus the value of risk at your previous weight, right? But both of them are the same thing now because you have your gradient 0, correct? So this delta is going to be 0. 0 is definitely more than epsilon. Your algorithm is going to stop. So it sounds it's working, right? Yeah? It's working. No, trust me. Everything you have, all these deep learning models you have trained, they all work with that. And it works. I mean, many people didn't buy it at the beginning, but it works. Yeah. Everything you have, all of those, ChatGPT is just using this. I mean, of course, with lots of details. And advancements, but at the end of the day, the idea is the same thing. So if you move in the minus direction, at some point you get your gradient 0. Where is the minimum? I mean, of course, it could be not your global minimum, but at least it is a local minimum, right? So that is the idea. And there is one thing here that is a bit crucial, and that is this eta thing that I put here. So what is eta? Eta is a number, right? Now, if my gradient tells me go in this direction, okay, I can go very slowly, or I can just take a very long step, correct? Yeah, so this step size is this eta value, right? So I just multiply my minus gradient to something. And that is what we call it learning rate. So now, should I choose it large? Should I choose it small? Any clue about that?
We can start with large steps.
Yeah, this is the usual practice. Exactly. But why we should do it? So it's a quite crucial thing, because if I have my function like this, if I move very large step, then I could just skip the minimum and get to a higher value, right? But if I move very tiny bit, then I just need to just move too much to get to the minimum, right? So I don't know whether I should choose it large or small, and this is the whole issue. So this is the problem that we have, and usually in practice we do schedule that, but we're going to talk about it in some good depth in chapter 3. Okay? I'm going to show you a few things in this chapter as well. Okay? But everybody got the idea of gradient descent? Yeah? Okay, great. So since you got the idea of gradient descent, let me quickly go through this particular, this tiny part, and then I keep that discussion on the learning rate later. Okay? So here, if you look at this algorithm that I showed you, what do I need to have is always I need to have the gradient. And gradient is a collection of your partial derivatives, right? So it means that the function that I have, it should have derivative, right? But do I have any function that I cannot compute its derivative? Do I have non-differentiable functions? Yeah, we have them, right? There are functions where you cannot compute the derivative. Can you think of any of them? Step function is one, right? Any other one? Is ReLU differentiable always? No, it has an edge, right? Correct? So when your function has an edge, or it is discontinuous, it does not have the derivative, right? And what if you're at that point and you want to take the derivative? What should you do? So this is an issue which is really sometimes crucial. So I could have a function which is continuous, exactly like ReLU, right? It's continuous. When I start moving on the function, I never fall out of the function, right? I always go on it. But it has edge on it. So at that edge point, I cannot compute derivative. If I compute derivative from one side, it's going to be 1. From other side, is 0. So it doesn't have derivative, really. Or my function could be discontinuous, right? Like a step function. So when I move, when I get to 0, I just fall out of the function, right? So it's not continuous. I cannot always move on that. So this is the issue with this function. So if I have, but for the first one, the non-differentiable one, we can usually handle it easily. So what we can do, we can use, instead of the gradient itself, we can use something that we call it subgradient. And what does that mean? Looking at this ReLU function, okay? So if I am somewhere at the negative values of x, what is the derivative? So when x is negative, what is the derivative of the ReLU function? It's 0, right? So it's like this, right? And the function doesn't change when I move on it, right? Now, I get to the point 0. What is the derivative? It doesn't have any, because when I get to 0, first I'm like this. So if I just think of moving tangent to this function, I should move forward. But if I look at the next point on the function, it's going up, right? So from one direction is 0, from the other direction is 1, right? But once I pass that point, then from that point on, I am going to have derivative again, right? And that is now, what is the value? Positive. And that is, I mean, here is exactly x, right? So it's going to be 1, correct? So it's going to have such a derivative. Everything, everywhere before is 0, everywhere after is +1, but there's one point in between which I don't know what to do, right? So the thing that I can do, I can put some value between 0 and 1 here, and then I call it subgradient. And what is the idea here? The idea is that, well, if I wanted to just move on this function, when I get here, basically, if I move on this line, or any line which is starting from being horizontal up to the exact line y equal by x, all of them are going to do the job for me, right? On all of them, I'm going up and lying on this function, right? But if I move any further, then I'm going to just get drop from the function, right? So this is the idea. So any line, I mean, in definition, any line that is touching your function at that particular point and is lying below your function, you can take the gradient of that line and put it as the gradient for your function. Yeah? So even though your function does not have a gradient, you can compute something, this thing, which we call it the subgradient. Okay? So as I said, like you think of any line which is touching your function and it is below it. So it could be this line itself. You could gradually store, and then you get to the y equal by x, right? But if I increase the tangent here, then it's going to just cut the function, right? So I'm going to get slope larger than the slope of the function that I have, right? And that one is not acceptable, right? So basically it means any point between 0 and 1, you can choose it, right? It's not going to harm your algorithm. It's going to, at the end of the day, work. This is why many people do not call it simply gradient descent. They call it subgradient descent. Because if you remove the function, the gradient, and replace the subgradient, mainly in the cases where you do not have the gradient because of your function being edgy, it's still going to do the job. It's still going to minimize your function or maximize your function, depending on what you're doing. Yeah? Everybody's clear? Yeah? So this is the idea of subgradient, but in the case where we have discontinuous function, we cannot do it anymore. And the reason is that basically at that particular point where your function is discontinuous, your gradient or your derivative is infinite, right? Because if I get very close to 0 on the step function, for instance, and I just move it tiny bit, as small as you want to think, then I am going to pass 0, right? So if I am at point 0, and I pass tiny bit, okay? It doesn't matter how tiny I move, I always get to the value 1, correct? So the new value of function is 1, the previous value was 0, this difference is always 1, but my step size could be very small, and this guy goes in the denominator, it just booms the derivative up, right? So you can essentially say that I have 0 gradient everywhere on this step function, but at this point, I am changing infinitely, right? And this is something we cannot deal because infinite doesn't make sense to us, right? So this is something which is a crucial thing, and usually in practice when we are designing our model, we try to have such functions as least as possible because at the end of the day, we are going to use gradient